real quickly review what we just did. Look at an example, or I don't know an example, but just illustrate, okay, how are we going to set up an integral on each of these circumstances. Suppose we have this and this, let's call that F and that G. First of all, are we going to integrate this one dx or dy? And we're not sure. Let's think about a sample element that would be dx and a sample element that would be dy. Dx, because we want to choose the direction such that we always have one function at the top, a different function at the bottom. Notice if we chose dy, this function is on both ends. That both ends are touching the same curve. We need our ends to touch different curves. So our change is in the x, so we're going to integrate dx. So since we integrate dx, if we call that one g and that one f, which one do we need to write first, G or F? You know what? I label the same curve both times. If we call this one G, this one F, that's the top one, G minus F. And we would go from this side to this side, so we'll just call that A to B. And the way, if it didn't give us those values, the way we would find those is we would find out when those two functions were equal. Now let's look at another case. On this one, do we need dx or dy? Right. There are times that a sample element dx does touch both functions. But notice there are also times where if we were to draw the sample element with dx, that the ends touch the same function. We can't have that. So we have to use the dy. So we're going to integrate dy. Let's call this one F, this one G. So which one is going to come first, F or G?
G.
Right. This side is F, this side is G. So it's always the larger minus the smaller. The further to the right, the larger. So F minus G. From here to here. We could call that Y1, that Y2. It's not the x value here and the x value here, it's the y value because we're dy. So whatever this y value is and whatever that y value is will give us A to B. All right, so that's area between two curves. In 7.2, we're going to look at volume. And there are two different approaches to looking at volume. The one we're going to do today is called the disk method. The one we're going to look at on Monday is called the shell method. in our project that we're going to do, we're going to use the shell method. There are some problems that using the disk is easier for. Some problems using the shell is easier for. So the way that we're going to get volume is we're going to start with a curve. Let's just look at a standard parabola from 1 to 2. So that just gives us an area. But if we take that curve and rotate it around the x-axis, it's going to give us a volume. Now let's see if I can illustrate that using Inventor. Let's create a 2D plot. And let's see, let's close that in. All right. So let's take that and rotate it. Take that area and let's just rotate it along the x-axis. You start that, and if you take it and rotate it, notice you get like this horn or like a bell. You can see that okay? So we can generate that by taking just a plain curve and rotating it. The thing is, we can rotate it different ways. We rotated that around the x-axis. We could take that and rotate it around the y-axis. Notice if you do that, you have this hollow looking shape. Kind of got a dip in it. Still, we could rotate it around even more axes. Let's say we came over here, drew a vertical line over here. So we can rotate it. If we have a shape, we can rotate it around any axis. Now, all of our axes that we're going to use are going to be either vertical or horizontal. We're not going to have any axes that are like slanted. But just from that one curve, we can generate lots of three-dimensional figures that have a variety of volumes to them. So the question is, well, how are we going to get the area or the volume of those? So let's look at, let's see if I can. Let's look at a sample element. So if we were thinking about the area of this, if we wanted the area, and we call this function is just a basic parabola, y equals x squared. If we wanted the area, we would go from 0 to 2 of that function dx. And basically, again, what we're doing there is we're taking a sample element, a rectangle that has some width, dx, some height that's given by that y value, which that y value is just f at whatever our x is. And the way we calculate our y is with this function x squared. So that's our y. That's our delta x. So we're just adding those up as we go, and that's how we get area. But if we take that sample element, that same sample element, and rotate it, it turns into a disk. So let's see if we can draw that. Let's come back. And if we take a sample vertical element, dx, and we rotate that, let's rotate it around the x-axis. You just get a disk. The volume of that disk we think about our disk. What shape is that disk? The cross section is a circle. Just to rotate. Yeah, the cross section is a circle. How do you calculate the area of a circle? That circle has a thickness. We call that thickness dx. And anytime, we discussed this back in, when did we do this? Cell 1. When we were looking at different volumes. If you have the same cross-sectional area throughout the shape, like here we have that same size circle throughout that thickness, the way you calculate the volume of that is you take the area times the length or the height of it. Well, our area of that is pi r squared. The height or the thickness of that is just dx. So if we want the volume of that one disk, it's just pi r squared delta x or dx. If we want that entire volume, we add all of those up, so we integrate from the left side to the right side. Pi r squared. Now, pi is a constant. So we can pull it out. R is the distance from the center to the edge. So if we were to take this sample element and rotate it, when it's straight down, it'll look something like that. So notice our radius, in this case, is just that distance, which in our case is just f of x. The key on all of these is going to be in figuring what our radius is. Because if you think back to our example, we used one function over one interval, and we got like 4 different volumes, didn't we? Well, the thing that's different about all of those is all of those had a different radius. So the radius is always going to be the distance from your curve to your axis of symmetry. And I butchered that. Doesn't that have 2 M's in it? Yeah, something like that. So let's look. Suppose we have f of x equals x plus 2, and we want to rotate that around the x-axis from 0 to 3 in the x direction. So if we think about this is a straight line with a y-intercept of 2, a slope of 1, and we're going from 0 to 3. So that's our area that we're rotating around the x-axis. So our sample element is going to go from our curve to our axis of rotation. Our axis of rotation is here. So that distance is going to be r. Well, if our axis of rotation is the x-axis, what is the y value here? The y value. What's the y value here? 0. The y value here is just our function. Whatever the value of our function is there. So that radius is given by our this y value minus this y value. So just our function. So our radius is x plus 2. Notice that our radius is a function because the radius here is different than the radius here. Notice as our x changes, notice our radius is getting larger. What is our radius here? The actual value of it? 2. What's the value of our radius here? Let's see, the x value here is 3, so if we put 3 into our function, so what's that distance? 5. From 0 to 5, it's 5. Is that right? So this is just a function that you tell me what the x value is, I'll tell you what the radius is, the distance from there to our axis, or our axis of rotation. So if we had 2, when x is 2, our radius is 4. So our volume is pi times our radius squared dx, going from this x value to this x value. Well, to get that, we would need to square x plus 2. The shortcut, remember, to squaring that is to square the first, take their product twice, and then square the last. Then to integrate that, that's just a polynomial, so we integrate each one. So the integral of that is x cubed over 3. For x squared over 2, which is 2x squared. The 4 picks up an x. And we're going to evaluate that from 0 to 3. So if we plug a 3 in, we get 27 over 3. 3 squared, 9, that's 18. 4 times 3. Minus, if we substitute a 0 in, we get 0, 0, 0, so 0. So we get for our volume pi times 9 plus 18 plus 12, which is 39 pi. That's the volume given by taking that particular cross-sectional area and rotating it around the x-axis. So let's see. Let's just or something similar to that. Let's see. What was our? What equation did I do? X plus 2. X plus 2, so 0, 2. And then we went, let's see. We went to the right 3. I bet that did the wrong way. Yeah. Let's first start that back. Yeah. Let's try that again. So we want to go. All right. So if we close that in, now let's rotate that around the x-axis. Then that's the shape we got. Now, if we just change that problem just a little bit, let's take that same function x plus 2 from 0 to 3. Let's rotate that same curve about the line y equals 7. I'll tell you what, let's do a different one for now. Let's do y equals 5. So we have this curve, and we're going to take that area and we want to rotate it around y equals 5, which y equals 5 is right here. Now, we have a touch of an issue here. Let's illustrate real quickly what that's going to look like. So if we take that and we rotate it around that, notice there's a hole in there. See that hole? So if we have a hole, we're still going to use our same basic approach, but we have to make a slight modification to it. And while the general process is called the disk method, when we have a hole in there, we actually use what's called the washer method. Now let's illustrate this. Let's suppose I take just a sample element here and I rotate it around the x-axis, then I get a disk. Well, if I take a little bit out of this, and I still rotate it around the x-axis, if this is the center of our rotation, this is the top edge, we're going to have a hole in here. And if that's just a sample element, that's basically going to look like a washer. So to get the area of that washer, the easiest thing to do is to think about, well, what would the area of this entire circle be? If we take that entire circle, the area is pi times that outer radius squared. Then if we could take away this inner area, let's call that A inner. Let's say it has a little r for the radius, then its area is pi little r squared. Of course, if we think about that as a volume, if now it has a thickness dx, then the volume of that outer region is pi r squared dx. The volume of that inner region is pi little r squared dx. So the actual volume that we want comes from taking the difference of those. If we take that whole volume and then subtract the whole out of it, then the remaining volume is pi r squared dx, the integral of that. Minus the inner volume, pi little r squared dx, which if we write that as a single integral, that's pi r squared minus pi little r squared dx. Factor out a pi, so the outer radius squared minus the inner radius squared. So that's called a washer. So if we think about our figure, let's think about this in two pieces. Our outer radius, if we were to rotate this whole thing, notice that our outer radius doesn't change. Our outer radius is the same throughout the entire thickness. Our outer radius is here. Our inner radius is this distance. Does that distance change? If we're going from 0 to 3, is this distance the same here as it is here? No. Well, let's look at our outer radius. What is our outer radius here? What is this distance? 5. Our inner radius is this distance, which is just this y value minus this y value. This y value is a constant. This y value, whether I pick my rectangle here or I pick my rectangle here, this y value here is 5. But this y value is given by our function. So this y value is just whatever f of x is. So our little r is the top minus the bottom. So 5 minus x plus 2. So our little r, 5 minus 2, so 3 minus x. So our volume is pi times, when we rotate. Let me see. Like when we generate our solid, this is all going to be air. When we take this and rotate it around this line, all of this that's colored in, that's going to be part of our solid. But that is going to be our hole, because we're not including that area in our rotation. So basically what we're doing is we're calculating the volume of rotating this around it, which is pi, the integral from 0 to 3 of this outer distance, r, which is 5 squared. And then we're subtracting the whole out of it, which is pi times that inner distance, which is 3 minus x squared. Let's do another one. Let's use that same function, but let's change our axis and see how that affects our r. So the region that we're rotating, we're taking all of that and rotating it. This time, let's take all of that and rotate it around this line, y equal -2. So in the problem, they're going to tell you what region. They're going to say, rotate the region bounded by these equations. So they would say, we want the region bounded by this, and we're going to rotate that around this axis. So if we rotate this around that, is there going to be a hole in the middle? Yes. So that's where we use our washer. Which basically when we use our washer, when we do pi big R squared and do that integral, we're including all the way from our outer radius to the inside. We're including all of that. When we do pi our little r squared, where we're taking that part, we're getting rid of that part. So it's still basically the disk method. We're just taking the volume that we would get from our axis all the way to the outside and subtracting volume from there to the bottom. So our big R, if we draw a sample element, it goes from the axis to the outside. So as our X changes, is that R going to change or is it going to be the same? It's going to change. If I draw my sample here, or if I draw it over here, notice it has two different lengths. So our big R is going to be this Y value, which that Y value just comes from our function, minus this Y value. And what is this Y value down here? Well, let's see, this is the x-axis. So -2. So the top one minus the bottom one. So our outside radius is x plus 2 minus a negative, so plus 2. It's always a good idea to pick an x that we know the distance and see if we really get the correct radius. When x is 0, our y is 2. So if this is 2 and this is -2, what's that distance? 4. If I put a 0 in for x, what do we get for the radius? 4. Over here, x is 3, y is 5. So from 5 down to -2 is how far? 7. 3. Yeah, 5 and -2 is 7. So if we plug that x value in 3, we get 7. So that function gives us that distance. Our inside radius is the distance from the axis to the edge of our hole. This time, from our axis to the edge of our hole, is that the same distance, or that's a constant distance? What is that distance? Well, the distance would be just 2. If we think about the y value here is 0, the y value here is -2, take the top minus the bottom, so 2. Once we get our big R and little r, then our volume is pi times our integral from left to right, big R squared minus little r squared dx. All right. When we rotate this around that way, all that's going to be a hole because this is empty. If we come in, let's see. Let's see. Let's put a line roughly there. We rotate that around that line. That's what it would look like. That makes sense. If we take right, yeah. As we rotate that, since it's diagonal, that's what makes our edge slanted. Because our cross section is just this piece. From this is the x-axis, this is our axis of rotation. There's nothing in there. And that's just by the way we defined our region. If we would have defined our region differently, then we might have had stuff in there, or we might not have. Let's look at they give one, let's say, y equals x squared, y equals the square root of x. So let's say find the volume of the solid formed by revolving the region bounded by these graphs around the x-axis. So our region is bounded by these curves, and we're going to rotate that around the x-axis. So let's first of all look at what our graph is going to look like. Y equals x squared is your basic parabola. Y equals the square root of x. If we put a 0 in for x, we get a 0. If we put a 1 in for x, we get a 1. If we put a 4 in for x, when x is 4, we get a 2. If we were to put a 9 in for x, we would get 3. Basically, that's a sideways parabola. So that's the region we're talking about. So if we draw that a little larger, notice, let's see, this one is y equals x squared. This is y equals the square root of x. Several ways we could solve this. If we wanted to find their intersections and we had not drawn a graph, we would set those two equal to each other. How do we get rid of a square root? Square both sides. So we would get x equal x to the fourth. So set that equal to 0. Factor out an x. That's a difference of cubes. If we factor that out, we get x minus 1, x squared plus x plus 1. So the intersections are when x is 0 and x is 1. So those are our points of intersection. So they say to take this, rotate this around the x-axis. Notice all of this area in here is going to be basically air in the inside. The area that is bounded is that. So we're going to have a hole. So our outside radius, that's from our axis to the outside edge. This y value is given by whatever the square root of x is. This y value is 0. It's always the top y minus the bottom. The little r is the radius to the inside, so from here to there. So this y value, that's given by x squared. This y value is 0. So big R and little r. Volume we get from pi times the integral from our left to our right, so from 0 to 1, of our big R squared minus our little r squared. The square root of x squared gives us x. X squared squared is x to the fourth dx. Then, of course, you have to evaluate that integral, the x to the fifth over 5, and substitute in. So that's if we rotate that around the x-axis. If we rotated it around a different axis, Let's get our little r's and big R's. If we rotated it around here, rotating it around that, let's call that y equals 3. Then our big R goes from our axis to the outside of our figure. And it's this y minus this y. What is this y here? 3. This y is given by this equation, x squared. The little r is the distance from the axis to the inside edge of our region. So this y, 3, minus this y, which is given by the square root of x. Then it's still the integral from 0 to 1 of pi times the integral from 0 to 1 of big R squared minus little r squared. Now, all the ones we've done so far, we've rotated around a horizontal axis. Real quickly, let's rotate around a vertical axis. Let's take that same figure, this is y equals the square root of x, y equals x squared. Let's take that and rotate it around the y-axis. So we're still taking the region bounded here. But our outside radius is from here to here. The inside is from there to there. So let me ask, are our elements going to be dx or dy elements? Dy. Which means that for our functions, our variable needs to be y. Here, our variable is x. Here, our variable is x. So we need to solve our equations for x so that our variable is y. How do I get x by itself here? We square both sides. This tells us that x is y squared. That represents that same curve, but now our variable is y. How do I get x by itself here? Square root of both sides. So this x is the square root of y. You give me a y, I'll tell you what the x is. So our big R, which now, instead of being a function of x, is a function of y, it's the larger x minus the smaller one. So our x here is given by the square root of y. Our x here is given by 0. That's big R, that's little r. Little r is this distance. Well, this edge is given by that. So in terms of y, this edge is y squared. This edge is given by 0. So that's little r as a function of y. That's big R as a function of y. So our volume would be pi times our integral This time, since our variable is y, we're going from here to here. In this case, since that point is 1, 1, we're still going from 0 to 1, but now that 0 and 1 are y values. Our big R is the square root of y, and that gets squared, minus our little r, y squared, which gets squared. Which turns out that's the same volume we would get. Let's see, we already erased it. But when we did that around the x-axis, because that's symmetric. This shape is symmetric. And it's the same distance here as it is here. So the key on all these is coming up with our R's. Always remember that our radius goes from our axis out to our edge. Or sometimes we'll say that our radius is perpendicular to the axis. If our axis is this way, our radius is that way.